Hello, and welcome to the TI Precision Lab covering frequency domain analysis for data converters. This video will introduce the fast Fourier transform, or FFT. The goal here is to provide an intuitive understanding of the FFT, and the deep mathematical background is intentionally omitted. The concept of windowing the signal to minimize error sources is also introduced. Here we show the mathematical relationship for the Fourier transform and the fast Fourier transform. The Fourier transform is a general method for taking a time domain equation and converting it to a frequency domain equation. The fast Fourier transform, or FFT, is designed to efficiently take discrete time domain data and convert it to frequency domain data. Since the FFT is designed to be used with discrete time data, it is commonly used to convert ADC data from the time domain to the frequency domain. We will not dig deeply into the math here, as there are entire textbooks on the subject. Suffice it to say that for n number of time domain points, the FFT transform will produce n number of frequency domain points. In the next few slides, we will cover some basic concepts with FFTs to give a better intuitive understanding of the subject. Here we show the time domain and its associated FFT, or frequency domain representation. First, the mathematics behind the FFT assume that the time domain signal continues to infinite time. The time domain signal at the bottom contains 16 samples. The FFT assumes that these 16 samples are infinitely repeated. Second, the number of points in the FFT are equal to the number in the time domain. In this example, the time domain has 16 samples, so the frequency domain also has 16 samples. Third, the FFT contains a region called the alias. The alias is a mirror image of the valid frequency region, and it occurs above the sampling frequency divided by 2. In this example, the sampling frequency is 1 MHz, so everything above 500 kHz is an alias. The alias region is normally hidden as it is redundant information. We will discuss aliases more in detail later. Fourth, all FFTs have a frequency resolution that is equal to the sampling frequency divided by the number of samples. The frequency resolution is the minimum change in frequency that the FFT can detect. In this example, the frequency resolution is 1 MHz divided by 16, or 62 kHz. Thus, the measured frequency bins step in increments of 62 kHz for this example. This slide is to emphasize that the alias region of the FFT is the mirror image of the signal frequency region. In this example, a square input wave is applied. This square wave has some odd harmonics. Notice how the mirror image of the frequency response shows up in the alias region. Again, this region is often hidden in many different FFT software displays as the information is redundant. Let's step through some basic math for an example FFT. First, notice that we have a 1 MHz data converter sampling rate. Next, we collect a total of 16 digitized time domain samples. The frequency resolution for this FFT is 1 megasample per second divided by 16, or 62.5 kHz. The time required for each sample is calculated as 1 divided by the sampling frequency, or 1 divided by 1 MHz, which is equal to 1 microsecond. In this example, the time domain input signal is a 125 kHz sinusoidal waveform. Translating the time domain sine wave to the frequency domain will create a component in a frequency bin. The frequency bin is determined by dividing the input signal frequency by the frequency resolution, which in this case is 125 kHz divided by 62.5 kHz, which is 2. Notice that in this case, the frequency bin is an integer because the input frequency is an exact integer multiple of the frequency resolution. So the sampled signal generates a frequency component in the second bin at exactly 125 kHz. The math for the translation works out nicely in this example, as the frequency bin is exactly 2. For this example, we increased the input frequency to 187.5 kHz. Again, this frequency happens to be an exact integer multiple of the frequency resolution, so it creates a frequency component in bin 3. However, what happens if the input frequency is not an exact multiple of the frequency resolution? This slide shows what happens when the input frequency is not an exact multiple of the sampling frequency. In this case, all the math is the same except that the input frequency is changed from 125 kHz to 180 kHz. Calculating the frequency bin for 180 kHz gives a frequency bin of 2.88, so it's close to 3 but not exactly 3. This results in smearing the frequency components into multiple bins. The tallest frequency component is located at bin 3, and other frequency components show up in adjacent bins. This smearing of the frequency domain signal is called spectral leakage. Spectral leakage is problematic as it is indistinguishable from noise near the signal. Remember, the FFT assumes that the time domain signal continues infinitely in time. However, practical real-world signals always contain a finite number of points called a record. The FFT copies and repeats each record infinitely. If the time domain signal is an integer multiple of the sampling frequency, then each record will connect smoothly to the next record. On the other hand, when the signal is not an integer multiple of the sampling frequency, the repeated waveform will not smoothly connect to the previous waveform, and there will be a discontinuity. The time domain waveform at the top shows the discontinuity between each record. This discontinuity is what creates spectral leakage. One approach to minimizing the spectral leakage is to use a time domain windowing function. A window shapes the time domain signal to force the time domain signal to 0 at the end of each record. The figure at the bottom shows the effect windowing has on the figure above. Notice that the discontinuity is masked because the window forces the function to 0 at the discontinuity. The objective of windowing is to minimize spectral leakage. The window has a frequency response and function like a bandpass filter. The main lobe in the frequency domain window passes the fundamental, and the side lobes attenuate the spectral leakage. This graph shows the frequency response for several different filters. Ideally, the main lobe, analogous to the passband, would be very narrow, and the side lobes, analogous to the stopband, would have a very high attenuation. In practice, windows with good side lobe attenuation will have wider main lobes. For the purpose of ADC analysis, the wide main lobe isn't a significant problem, so the 7-term Blackman-Harris window is used to achieve the least amount of spectral leakage. FFT windowing is not just used for ADC characterization, but is used in many forms of analysis. Depending on the type of analysis required, different types of windows may be required. This table lists different types of windows and an example of what type of signal content this window is optimal for. For example, a uniform window is optimal for measuring white noise. In general, we will be using the 7-term Blackman-Harris as we are using the FFT for ADC characterization. Since the window function modifies the amplitude and frequency response of the sampled data, there are some associated processing errors. This table summarizes these errors. In most cases, these error terms can be accounted for and corrected in software. This is taken care of automatically in our evaluation module software. Let's look at each error source. Processing loss is the reduction in SNR due to the signal spreading across the main lobe width. Because of this spreading in the signal power, a gain correction factor must be used to accurately compute SNR. The processing loss assumes the frequency of the test signal falls exactly in the middle of the frequency bin. Since the input frequency may not match exactly the frequency bin in a non-coherent test setup, the scalloping loss is the perceived signal attenuation in the FFT when the signal frequency component falls exactly between bins. The worst case processing loss is the sum of the processing loss and scalloping loss, and it provides a measure of the maximum SNR reduction due to the window function and the worst case frequency location. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content.